Hanson, engage.
I have to answer that question.
I'll answer the question. You want answers? I think I'm entitled. You want answers? I want the truth! You can't handle the truth!
Give us some men who know the truth. And who will declare the truth. And who will stand with Athanasius and Polycarp and Calvin and Luther and Whitfield and Edwards, and who will declare from the housetops that the gospel is the power of God unto salvation.
Welcome, everybody, to the Engaged Truth Show. I'm your host, Caleb Harrelson, and on this show, we make the case that Christianity is total truth for all of reality, and I believe even the rocks cry out the glory of God. And tonight, you're in a special treat, as we're going to see exactly that the rocks point to and confirm the story laid out in Genesis of the global flood. And I'm so excited to bring to you guys tonight a very special guest, Dr. John Whitmore, and I'm going to go ahead and bring him on here on the show here. Dr. Whitmore, how are you doing tonight?
Hey, I'm doing pretty good, Caleb. Nice to be with you tonight.
Well, it's so good to have you, and I've heard so much about you from my friend Nate Loper, and we've had on the show several times, and he gives tours with Canyon Ministries, and you guys check those videos out, and I hope you guys go get a tour with him as well. And I know you do tours with Canyon Ministries as well, is that right?
I do. I've been on several trips down the river with Nate. Really good guy. So
yeah, oh, that's awesome. And now currently you're at Cedarville University as the geology professor. Is that correct?
Yes. Myself and a colleague, we have a small geology program at Cedarville. We started that program in 2009, and we have 40 plus graduates out of that program now, and they go do all different kinds of things. We've put a number of those students through various graduate schools around the country. We have some PhDs now, a couple more in the pipeline. We've put geologists in environmental positions in industry and things like that. So doing all different kinds of things.
Oh, that's awesome. And man, I think your students are just spoiled in so many good ways, and it sounds like they're getting amazing education. I watched one of your recent chapel talks on geology. I was like, isn't this amazing? You're getting geology in a chapel talk. Now, how did you even get into this subject of geology and creation science?
Yeah, I started collecting fossils as a kid, and that's really opened my eyes up. And then in junior high, went around the state of Ohio collecting fossils, and live right nearby now, a place where I visited even as a kid, and still go back there and take students back there to collect fossils. So it's a lot of fun. We like to get our students out in the field and see the rocks. That's the most important thing for a geologist, to get outside and actually see and touch and feel the data. So
yeah, I know you've told me about a recent trip, and I've seen you take students to the Grand Canyon a lot. Is that right?
Yeah, just last week I had a group out in Arizona, Utah, Nevada. So we went before the semester started because of COVID. We're kind of restricted where we can go. So we got permission to go before classes began. So we spent a week out in the field learning about rocks last week. So.
Oh, that's awesome. And, that's what one many things I respect about you and your work is you're out there doing a lot of field work, and man, you don't have time to be doing debates online, but because you're actually getting into the data and digging into that. Yeah. And one of the things I am excited to have you on tonight to talk about is the Coconino Sandstone and how that interacts with the flood, because I didn't realize till recently that this is a really big issue as far as the flood debate is involved. And I've asked some geology friends who are like, I haven't heard about that. But then when they've dug into it more, they'll see there's a lot of people are saying, oh, we think the Coconino Sandstone is just blown by wind, so it couldn't have been a flood. But you've done a lot of research on that.
And this is a big deal because conventional geologists think that Coconino proves the Bible is wrong, and we'll talk about some of that in some of the slides I have prepared for tonight. So,
Yeah, absolutely. And so I'm excited. Let's just dive in here, and
Yeah,
we'll go
very
ahead
good.
and add those slides to the stream.
Yeah, so this is a presentation that I gave a few years ago at the International Conference on Creationism. Paul Garner is my co-author, and he did a lot of writing and work for this report and this research. And this research is, I've been involved with it since late '90s, I suppose, in various ways. And this is kind of a summary paper. We have a lot of papers in both secular and creation journals that cover the research here. So I've got some references and stuff like that at the end. And I won't give a super formal talk tonight. We'll have more of a dialogue on some of these slides, Caleb. So if you have
Sure.
questions, go ahead and jump in, and maybe people online can text some questions in as well. But
Yeah, and we can highlight your comments and questions. Like here, we'll highlight Nate Loper. We see our buddies
yeah,
on here.
yeah, my buddy Nate, very good.
Yeah, so you
So
guys ask away in the comment section.
yeah, so Grand Canyon is a fantastic place to work, and Coconino Sandstone is right up there near the top of Grand Canyon. If you stand near the rim of Grand Canyon, you can see it, stretch down the canyon, both east and west, and it's a white rim kind of that runs along the top of the canyon. Fortunately, it's only 3 layers down. So as I studied it, we only had to go for about 1 hour hikes down into the canyon. You could get down to the bottom of the Coconino in about an hour. And so most times I've been down all the trails that have Coconino on them and taken a look at the Coconino in various places over the years in Grand Canyon. We've also looked at it all over Arizona. It extends into Nevada and New Mexico, is named other formations as it goes up into Utah and other places. But we've done some work on that as well. So you can see this nice white band at the top of the Grand Canyon right there. That's Coconino Sandstone. So I had some colleagues that helped me in the work. Ray Strom, such an integral part. Ray has a rock lab up in Calgary, and he processed almost all the samples, and he was such a critical part because in all the years people have been talking about the Coconino, nobody's looked at it under the microscope. And we collected over 400 samples, and Ray cut thin sections up in his lab so we could see the sandstone under the microscope. And we made so many discoveries, things that people never saw before under the microscope. And then Paul Garner is from England, so this is really an international project. United States, Canada, England, and Paul is an excellent field researcher as well. I wanted to work with Paul because there's some similar sandstones in England, and I was able to go to England with Paul, and Scotland and Wales as well, and see some other sandstones over there that are similar to Coconino. And Paul is an excellent writer too. Maybe you've read some of his stuff. He publishes a lot in various places. Has a really nice book, The New Creationism, that I read that. Students read. Yeah, good. And he's a really good writer. And then Guy Forsyth joined our team a little bit late, but he was instrumental because he actually lives in Sedona. So that's in Arizona. And he has Coconino Sandstone in his backyard. So he hiked all the hills around Sedona and actually found some really incredible folds in the Coconino that we'll talk about tonight. But this project was part of ICR's FAST project. The FAST project was about 2007 to 2012, so 6-year time span there. And ICR supplied a lot of the funding for travel and things like that, but also there were some other sources. So Ray Strom's lab in Calgary provided a significant amount of funding. And also I had some help from Cedarville and some other places too. And we are not the first ones to work on Coconino. Leonard Brand kind of cut his teeth on Coconino as a young geologist and scientist, and he's in his mid-70s now and still working on Coconino. Has worked on it almost his whole career, and he has done some really incredible work on the footprints that are found in the Coconino. So he has joined our group every now and then, and we've done field work with him and things like that. This is what the Coconino looks like in Grand Canyon. This is down Grandview Trail. It's a cross-bedded sandstone, and so you can actually see the layers in the Coconino at an angle right here, and you can see the layers down below there, Caleb, are flat, and the flat layers down there, that's part of the Hermit Formation. Okay. And so you can see the difference between a cross-bedded sandstone and a rock that's has horizontal layers in it. Now you might want to, people might be wondering, why study the Coconino sandstone? And the reason it's really important is that the Coconino is kind of like an example or a type sandstone that geologists look for. And in 1934, Edwin McKee came to the conclusion that it was a windblown sandstone, that the Coconino sandstone represented fossil desert sand dunes. And so it's a really well-known sandstone, and as we'll talk about, a lot of people use the Coconino as an example that the Bible is wrong. And so they think that these crossbeds in the Coconino actually represent desert sand dunes. And of course, you can't have desert sand dunes in the midst of a global flood. So we think the Coconino is deposited about midway through the flood record. And so as a creationist, we'd probably think that it's water laid. Now, as scientists, we go out with open minds and take a look at the Coconino. I had done a lot of reading on the Coconino before we even got out in the field to kind of see what we're up against. And actually, at the start, I was a little worried. I had read all kinds of stuff about the Coconino, and I was wondering, what are we going to find when we get out into the field? But, we ended up finding some really great things, and I believe God had a hand in that, led us to various outcrops and collected significant samples and so on. But it's important because it's in the Grand Canyon. It's in one of the most visited national parks that we have in the United States. And, people want to know, how the rocks got there. And so it's an important formation to study.
Absolutely.
So here's what it looks like again in Grand Canyon. This is kind of what it looks like up close. It's the third formation down. So we have Kaibab limestone up here at the top. This little slope in here is the Toroweap Formation, and then this is Coconino. It doesn't look very thick there, but it actually is about 300 feet.
That's
so
pretty
it's
thick.
it gets a little thinner as you go up toward Utah. It gets a little thicker as you go down toward Sedona area. It's maybe almost 1,000 feet thick down near Sedona, so it increases significantly. But it's pretty well known. It's well cited in the literature and so forth. And again, it's this example of a desert sand dune, according to McKee and lots of others. McKee is probably the most famous Grand Canyon geologist. He started his career in 1934 by writing a paper on the Coconino Sandstone in Grand Canyon. And that was the first of many different papers that he wrote about Grand Canyon formations. And so a lot of people, respect him. He was an excellent geologist, and, they of course look to his opinion on an important rock formation like this. So here's another example of what crossbedding looks like. Here are some angled layers in the Coconino Sandstone. This example is over near Holbrook, Arizona. But here's the reasoning. People think that sand grains bounce up a sand dune. They collect up here at the top of the sand dune and then avalanche down the backside. And the wind would be here blowing from left to right. And so people would look at these crossbeds in the Coconino and say that these are the slopes of desert sand dunes. And I did this with my students last week. We're in some small sand dunes outside of Las Vegas, and you can actually measure the angles on the avalanche slope, and they're right around 33 to 34 degrees, and they don't vary very much away from that. And so that's what most geologists expect. If you go look at, sandstones that have been fossilized, desert sand dunes, they should have fairly steep crossbeds. And that's what I read in all the literature. And I'll tell you what we found in a little bit here. The Coconino has these crossbeds, and scientists think that these beds actually climb on top of each other. So you actually get a pretty complex set of crossbeds in these sandstones. This is really being studied a little bit more to see if this actually happens. And some sand dunes have actually been bulldozed through to see what the patterns are inside, and the patterns turn out to be a lot more complex than what we see in the Coconino. So this kind of pattern we see in the Navajo and the Coconino, but you take a look at real sand dunes, which you don't get a chance very often to look inside of sand dunes, but it's been done in a few cases and tends to be a little bit more complex than what we see here.
Now, you said these wind-blown sand dunes are 33 to 34 degree angle. Is that right?
That's right. Yep.
Okay.
And I'll show you some measurements we took on the Coconino. Here's a sandstone that's correlates with Coconino. This is the Deshay sandstone in the eastern part of Arizona. And you can see these flat bounding surfaces in here, and they separate the layers of the crossbeds. And you look at this, and when you're on site, you look at them and say, oh, those are really steep crossbeds. And I've had people on river trips and other people, I ask them, estimate the dip for me. And then I lay a compass on there, and they're shocked that the dip isn't higher. So we'll look at some measurements here in a few moments. But the Coconino, I've traced this out, and I've published some papers on this since I made this presentation in 2018. But the Coconino actually extends across most of the western United States. I've been able to correlate it all the way up into the Dakotas. It's not called the Coconino everywhere. It's not always cross-bedded, but I've been able to trace a sand that's equivalent to the Coconino throughout all these states. And so I think we need to look at this as a sand sheet, sheet of sand or a blanket of sand across the western United States. Crossbed dips, I found out, all tend to go pretty much to the south and oftentimes to the southwest. But crossbed dips throughout all these sandstones. It's not just in the Coconino. And that's another thing that kind of ties all these things together, is a uniform crossbed dip. But again, it extends. I've been able to trace it all the way up into the Dakotas. Pretty amazing blanket of sand.
So you're saying they're dipping at a south to southwest angle. So is that the current flow when it's being laid down?
Yeah, so that would be the direction the current is moving, whether it be wind or water. The crossbed, the way that the crossbeds dip will show you which way the current was moving the sand along. So we think
that's amazing.
The sand was going from north to south. Actually, we've been able to trace little minerals in these sandstones called zircons. We've been able to trace them back to the Appalachians. I haven't done that work. Others have done that work and recently published it. But we know that a lot of this sand came from the Appalachians. How it got out west is a whole different story. I think water explains it a lot better. But conventional scientists would say by rivers or by wind it got to the western part of the United States.
Yeah, when I was in northern New Mexico, I was so excited about crossbeds when I understood their implication. Went up to the Glorieta Sandstone, and I just in their museum there, I read the secular geologists, and they basically said it came from the Appalachians, but we think it was windblown.
Yeah, and that's kind of interesting, especially when you look at some of the minerals in the sand. because the most of the sandstones are made of quartz. You look under the microscope and you see mostly quartz grains, but there's some other minerals in there too, and the other minerals cannot survive wind-blown activity, and so we'll talk about that in a few minutes. So there's been a lot of talk on coconino, and I have just a couple of the quotes and references here. Just to demonstrate, there's a lot of literature out there, and especially a lot of people have commented that, you know, the coconino disproves scripture. So this is a 1980 paper, I think it was in the very first edition of the journal Creation Evolution, and a guy named Weber here said that you don't need a PhD in geology to know that desert dunes and other desert deposits do not form under roaring floodwaters. These require not only time but also dry land. The flood of Noah supplies neither. The Permian Coconino Sandstones in the upper walls of the Grand Canyon have frosted, well-sorted, well-rounded sand grains found only in land-deposited sand dunes. And so here's a guy, you know, after reading what he said about it, I don't really think he looked at the Coconino Sandstone very carefully. He maybe read some other papers about it. But this is what happens about the Coconino. People make these statements, and you go look at the sand under the microscope, and these statements are not supported. So notice that I have frosted, well-sorted, well-rounded, highlighted in yellow. So we're going to look at the sand under the microscope and see if this is actual reality or not. Here's another quote by Strahler, and he wrote a book in 1999 that talks about a lot of different aspects of creationism and evolution. And he cites things like the Coconino Sandstone. He called it Coconino Formation. And also talks about the Navajo sandstone in this same passage. The Navajo is a similar sandstone up in Zion National Park. It has even bigger crossbeds than the Coconino, just a spectacular sandstone. But he says that these sandstones like this are, you know, windblown, and that because you have windblown sandstones, it proves that the flood account is wrong. And he says that. He says it in itself is sufficiently weighty to totally discredit the biblical story of the flood of Noah. And so that's one of the reasons I wanted to study the Coconino, is, you know, it's being used as a tool to say that Scripture's wrong. Now here's an interesting book. Davis Young and Ralph Sturley. These guys are Christians, but they're old Earth creationists. So they would believe in some type of creation, but they believe that the Earth is old and the Earth's rocks are old. And they talk about the Coconino in several places in their book. Again, they call it the Coconino Formation, which is incorrect, but it should be Coconino Sandstone as the formal name. But, you know, they say that the grains of the Coconino are all a uniform size. And why do they say that? They say that because desert sand dunes, if you take your hand lens and look at grains in a desert sand dune, you'll find that most of the grains are close to the size, because wind does a really good job sorting grains.
Okay.
They also say that mica grains are not present in the Coconino. Obviously, they have not looked at the Coconino under the microscope, because we're going to find all kinds of mica in it. And they say that the grains are well-rounded. And again, you know, how do they know that? They don't put any pictures of the Coconino Sandstone in their book. In fact, you know, when Sturley and Young wrote this in 2008, nobody had published any thin sections or microscope views of the Coconino. And so I don't know how they knew that. They say right there in the first line that a hiker can easily verify these things. And I've looked at Coconino with a hand lens, and I just don't see what they're finding. So we'll see here.
Very interesting.
Here's another quote from Young and Sturley, and they say that the Coconino has steeply dipping crossbeds. Notice that they say greater than 20 degrees. And they say that these dips are typical of windblown sand dunes. The name subaerial here, or eolian, refers to sand that's been deposited in deserts. So this fellow was fairly interesting guy. His name's Steve Newton. He used to have some YouTube videos and stuff on Coconino. Maybe he still does. I don't know. But he actually came and visited me at a national geology conference, actually several times, I think, and published some articles about us in Earth Magazine. He actually came on some field trips and did some other things, and wrote about the Coconino in a very clever way here. He said the Coconino sands stick in the eye of the creationist model. And he says that creationists are deeply committed to washing away this irritating formation by arguing that the Coconino could have been deposited in a marine environment after all. And of course, that's what we're arguing, that the Coconino is deposited in a marine environment, but we're arguing that not because the Bible says it does, or says it could be marine or should be marine. We're arguing that from the data. And, you know, that's what we've been presenting in the scientific conferences. Our conclusions are based on the data, and that's what scientists are supposed to do: go out and collect data and then interpret the data. And we argue that the data that we found strongly argues that the Coconino is made underwater and not in the desert. And so here's a lady that you can look up on YouTube. I don't know if her video is still out there. She was rather crass, but she says, you know, of all the rocks in the Grand Canyon, the Coconino is most likely to, well, how should I say it, make creationists worry the most, right?
Yeah.
And so anyway, she says that, you know, this enormous desert in the midst of your giant deluge is inconvenient. And she's right. And so, you know, we as creationists, I think, have been responsible scientists, at least in the matter of the Coconino. There's some creationists out there that aren't that responsible and don't do good science, but I think we've done some pretty good work on the Coconino, and we found some things now that we can throw back in the conventional community's lap and say, hey, you need to explain this in your desert model. We think it's going to be very difficult for you to explain this in your desert model. So we've kind of flipped the Coconino problem on its head, and now it's not a problem for creationists, it's a problem for the evolutionists.
Yeah, this is huge. What you're going to present tonight.
Yeah, and so one other book. This is a more recent book. This one was published in 2016, Grand Canyon Monument to an Ancient Earth, and it has a whole list of scientists that edited this. And as I read it, I was absolutely shocked at the poor science that they actually present in this book. They talk about the Coconino a lot. It's a centerpiece of their argument. But they make a lot of mistakes and actually ignore a lot of evidence that we've done and work that we've done on the Coconino that was actually published at the time, or published before this book was written. So these scientists should have actually known better. But there's you can see the different things they say in this book about the Coconino, and you can go check these things out. And we have things that, you know, and have published things that go up against each one of those things.
Oh, you said that. So there was some data that was published previously to 2016.
Yeah.
They must not have referenced or something.
That's right. We had been publishing short abstracts and some longer papers as well at Geological Society of America. I know some of these scientists. I talked to some of these scientists about these things, and, you know, they didn't recognize it in their book. And, you know, I have to ask why. You know, what was their motive for not, you know, talking about what we'd done? And so here's our research approach. We did our work in the library. So that's really important in any scientific project. You want to make sure you do your library work, find out what's been written on it, We search the literature. There's very good search mechanisms for the scientific literature. Most people do searches with Google, but scientifically there's much better databases to use, and we use those. But we also studied modern sand dunes. And so Ray Strom and I and my son, we went to a lot of different modern sand dunes in United States. We even looked at some sand over in Great Britain as well. We did a lot of field work. So we spent many months out in the field collecting samples, hiking, looking, studying the Coconino. And then you do that kind of stuff in the summertime, and then in the winter you analyze things under the microscope and work in the lab and stuff like that. And then when you do that, a responsible scientist is going to present their findings. And so we presented our findings at scientific meetings. We went to a lot of conventional scientific meetings, and we also presented at a lot of creationist meetings as well, because both groups of people we thought would be interested in what we'd found. And then after you present things at scientific meetings and get feedback and whatnot, then you write scientific papers for the scientific literature. These are not books. They're journal articles, scientific journal articles where they're peer reviewed and reviewed by other scientists that are familiar with the study. These things are ongoing. We just published some more papers just this year that, from our ongoing research. And there's been some others that have been working on this project besides me as well. But work continues to be published on this. And so what is the Coconino Sandstone supposed to look like? Well, everybody says that Coconino is supposed to be well sorted. This is not Coconino Sandstone over here. This is actually sand from a desert dune deposit. And you can see that most of the sand grains are almost the same size. Okay, so Coconino is supposed to look like that. Coconino is supposed to have round grains. Okay, like there's some really well-rounded grains in this photo.
You're saying what it would look like if it was windblown?
So what we wanted to think of, what I want people to think about is, as we go look at what we found, what should we expect if this was windblown, right?
Right.
And so if it's windblown, we should expect well-sorted sand. We should expect well-rounded sand. We should expect really steep crossbed dips. This is Great Sand Dunes National Park in Colorado. That's a 33-degree slope right there. And so we should expect those kinds of things. We shouldn't expect minerals like mica. Here's a flake of mica under the microscope right there. I've got it highlighted in red. So we shouldn't see that kind of thing in the Coconino. We shouldn't see dolomite in the Coconino. This is what's called an ooid. It's about the size of a BB, and you can see it has a round shape, and that's made of the mineral dolomite. Dolomite's a marine mineral, so you shouldn't be finding marine minerals in a desert deposit. You should find at the base of the Coconino maybe some mud cracks and some things like that. This is a dried up pond in Death Valley, so you might expect things like this to be down at the bottom of the Coconino. You might expect some various trackways. So if you go out to a desert, you find lizard tracks and snake tracks and insect tracks. And actually, they're pretty abundant. You don't have to look very hard for them in desert deposits. And then you should also find like raindrop prints. Here's some modern raindrop prints and some dried up mud right here. But you know what? Most people think raindrop prints should be like craters, right? Like we have in the mud, but raindrop prints in sand look like this. And you get this mottled appearance. And so we want to keep that in mind as we begin to look at some of the data. So what we're going to go through tonight, Caleb, is we found 10 myths related to the Coconino. And we found all this stuff published in the literature. So people say there's steep crossbed dips, well-rounded, well-sorted, mud cracks, and so on. And I'd like to actually show you what we found. So this is kind of what we were expecting to find, but we found that all these things were largely not true about the
Wow.
Coconino.
Huh.
And
That's astounding.
yeah, and we were actually surprised at what we found, and I could probably add a few more things to this list as well now. But the first thing are the crossbed dips. So we'd seen all this data that said that the crossbed dips are really steep. And so there's a tool that a geologist uses called the Brunton compass that you can lay on the crossbed and measure the angle. And it's very easy to do. In fact, most cell phones now can do this. We didn't make these measurements with cell phones. Cell phones weren't that good when we started all this research. But
So is that an app or something?
yeah, there's actually on the Apple phone, there's something that comes with the phone that you can measure an angle with. But I just lay it on there. But
Yeah,
here's
awesome.
here's all of our measurements, and I think we did this and all these measurements from maybe 2012. So we've got a lot more measurements since then. But our number here is this represents 214 measurements, and the average is about 20 degrees. And as we were doing all this research, I came across another paper published in 1938 in the Journal of Geology, a secular geology journal, and a guy named Reiche published crossbed dips from the Navajo and the Coconino and several other sandstones, and guess what his average was? 20 degrees.
Wow.
So there seems to be a theme here, right? And I have one of my students did her dissertation work at Loma Linda. She did a project on the Coconino. Guess what she found? And an average for all her crossbed dips, about 20 degrees.
Oh, wow.
And so, this is about, and there's an argument that says maybe there was a little bit of compaction that happened after the sand was laid down, but you can't compact the sand from 34 degrees down to 20 degrees without seeing some results. So if you compact it down that far, you're going to be breaking grains and diminishing porosity and doing some other things in there. And we just don't see that in the Coconino thin section. So, we think that, the original dip was maybe a few degrees more than what we measure, but it can't be, 34 degrees.
Yeah.
So here's an example of some crossbed dips. And this is out near Holbrook. And you might look at these dips and say, oh, they're really steep. And, some people, like in the Grand Canyon Monument to an Old Earth, they actually put a protractor on a picture like this and said, see, the Coconino dips are really steep. But you can't measure crossbed dips like that. You have to get a flat surface, so you can see this three-dimensional flat surface right here. And you can actually pour some water on the outcrop and watch the water run down dip right there. And that's the angle that you want to measure from the horizontal. And believe it or not, the dip in this picture, I think if I remember right, the crossbed dips in here were about 17 or 18 degrees.
But they used this picture in the book?
No, they didn't use this picture in the book. They used some other pictures from the Coconino, but this is just one example of where the crossbed dips are not that steep. And they might look steep, but when you actually measure it with the Brunton compass, they're not.
I have a good question related to the angles here. I'll pull it up. Fencer for Jesus says, so how are the mainstream geologists getting the 32 to 34 degree averages so certain? Are they just quoting their expectations and not actually measuring things?
I think that's exactly what's happening. They hear that the Coconino is a desert deposit. And so since the Coconino is a desert deposit, the crossbed dips must be really steep. And the problem is they didn't go back to the literature. They didn't look at Reiche's paper from 1938. I mean, it's been in the literature over 80 years, right? And, they also have not actually put Brunton compasses on the sandstone to measure it for themselves. And so they're coming up with this misinformation just based on their idea that this is a desert sand dune deposit, so the cross beds must be steep, and they're not.
Wow, that's so interesting. Your background research is so key when people are doing the
Yeah.
scientific method here.
You got to get out and look at it and actually measure. Now, here's an interesting thing we found. Here are some avalanche tongues. So you can see these tongue-like features. So the sand actually slides down these dunes, and these avalanche tongues are pretty narrow. They're only about that wide or so. When they come down the whole bit of the dune. So I have some arrows where some of these come down, but they come down as a three-dimensional tongue. So it kind of scoops out the slope as you go along. And we were, this is in Colorado, and this picture's in California. And I came to this area with my students a day after they had a heavy rain here. Oh, and the wind had picked up and polished off this dune right here. And so the avalanches actually take place down here. So this is the 33, 34 degree slope right over here. And the polished dune actually shows us the three-dimensional scoop of these things. You see these little cusps in here? Right. And so that, if you're able to look at a cross-section of a dune, that's exactly what you should expect. You should expect these avalanche scars to be preserved in the sand dune deposit. Well, you look at Coconino, and for the most part Navajo. I've found a few things like this in the Navajo sandstone, but never in the Coconino. You look at that surface right here, and it's just straight as an arrow. So here's several places where you can see these lines, and you can follow these lines nice and straight down the whole length of an outcrop. And same thing right here. Here's some feet in this picture for scale, but you can follow these lines straight as an arrow. The avalanche bed, the so-called steep avalanche bed, would be right over here. So you would expect to see these cusp-like things that we saw in the last photo in things like the Coconino, but they're not present. And so that argues to me, or that demonstrates to me, that these sand dunes, the cross beds accumulated it in some way other than what we typically see in a desert environment. So when you begin to look at the details of the Coconino, it does not match up to what we see in the deserts.
Wow. Yeah, that's fascinating.
Okay, so the crossbed dips, that was our first myth, or second myth. People have said over and over that the crossbed, that the Coconino has well-rounded and well-sorted sand grains, just like modern sand dunes. And so geologists have a scale for rounding and sorting. So the rounding can go from very angular grains all the way up to well-rounded grains. And you can have very poorly sorted grains up to very well sorted grains. And if you just go out to deserts and collect sand samples, you can find grains in all these categories, but most of the grains tend to fall up here near the top, either well-rounded grains or rounded grains. And as far as sorting, most of the grains tend to be well sorted to very well sorted. And what that means is that all the grains are the same size. Okay. And now we're going to take a look at what we find under the microscope. So what we find under the microscope for the Coconino is here. You'll see that the grains are mostly subangular, and you'll see the sorting is not so good. And so here's some microscope pictures of the Coconino. So what happens here to make this is we collect a rock sample, and we cut the rock sample very thin. We polish it down. And so you're seeing individual sand grains here. The blue is actually epoxy. It would be the empty space in between the sand grains. And take a look at these grains. This is a quartz sand grain. This white colored grain here is quartz, but you can see these sharp corners on it. Here's another quartz grain. You can see the sharp corners on it. And they're angular. And this is not what you'd expect in a desert deposit. And so I'm just baffled, by people like Young and Sturley, who say that, all these grains are well rounded. They've not looked at it under the microscope. And quartz is a fairly hard mineral on a scale of 1 to 10, called Mohs scale. It has a hardness of 7, so it's a fairly hard mineral. This yellow mineral right here is K feldspar. And you can see this is a softer mineral, but you can see that even the K feldspar is rather angular right there.
Mm-hmm.
And we've looked at these minerals in beach settings, and like along the west coast of the United States, you can find these minerals in the beach, and then there's sand dunes right there next to the beach. And just over the course of like the length of a football field, those yellow grains right there become round. It transported just that far. And so how in the world are these yellowish grains right here, these soft K feldspar grains, how in the world do they stay angular in this supposed huge desert? They should be well rounded, and they're not. And sometimes they're even more angular than the quartz grains, which is just befuddles me, how you can claim this is a desert deposit. All right, so the last slide showed you some things on the angularity, and you can see some angular grains in here too. But what this slide demonstrates, and you can see a bigger quartz grain right here that's a little bit better rounded than some of the smaller ones, and that's kind of typical for most sand grains. But the thing here that you see is that you see many grains of different sizes. And we call this poorly sorted grains, and you don't expect to see this kind of a mix in wind-blown deposits. Wind tends to sort grains out really well. And so this is pretty typical in the Coconino to see things like this.
Wow, that's so fascinating.
And, that was a surprise to us. When we started the research, we had no idea what we would find. And so that was kind of neat to see that. All right, here's something else. This was actually one of the first things I studied in the Coconino. I studied these sand-filled cracks. And here's one of the bigger ones. And you can actually see these along Bright Angel Trail if you hike down into Grand Canyon. This is fairly big. This one right here, to give you an idea of a scale in there, these are around 50 feet or so from the bottom of the Coconino right here, right down into the Hermit. And these cracks are actually filled with Coconino sandstone. And so here's the story that's told about this in the conventional literature. They would say the red formation down below is the Hermit Formation was a floodplain. So you have these floodplain muds that are accumulating. Everything dried up, and so you had these giant mud cracks that formed. And then the Coconino Desert blew in. And as the Coconino Desert blew in, it filled up these mud cracks that had formed. And so, I read the story and started looking at these things. And if the sand had actually filtered in from above and settled in from above, you should expect horizontal layering in these sand-filled cracks. But I went and looked at these, and I was not finding any layering at all. Nothing. And in fact, some of the sand-filled cracks, the layering was actually vertical. I'm like, what in the world is going on here? So I knew they weren't filled up mud cracks, but I wasn't sure what they were. And I started making measurements on these things, and these things go back into the outcrop at certain angles. I could measure that direction in many cases, but I also could measure this length right here. And what I recognized that there was a trend, and the very deepest sand-filled cracks were right next to the Bright Angel Fault. And I'm like, that's really interesting. And as you went away from the fault, the cracks get shallower and shallower, and they eventually disappear. And so I put together this hypothesis that the sand-filled cracks were actually generated by the movement of the Bright Angel Fault. And so this next slide kind of shows the pattern here. Oh, wait a minute. I have some more examples here. So here's another one.
Oh, nice.
Here's a 3-meter scale right here. That's about 10 feet. Here's another one. This guy standing here is about 6 feet tall. So you can get an idea, how big that actually is.
Wow.
And then here's the map that I made. These really big ones were right here. This is in the south rim of Grand Canyon. So if you hike down the Bright Angel Trail, you can actually see these. And the longer these triangles are, the deeper the cracks go. And as you go to the west, they disappear. So I went down South Bass Trail out here, kind of hard to get to, but I was there. And there's nothing out there. There's no sand-filled cracks out there. You go out here to the east, they get shorter and shorter. They kind of disappear out in this area. There's a few more smaller ones up in this area, but they're really, really tiny. And you go across to the north side, down North Kaibab Trail, and the cracks are there, but they're shorter. This red line indicates the Bright Angel Fault. And what's interesting is the fault moved more on this side. I think in feet, it's about 200 feet or so. And this end over here is maybe 60 feet, I think, if I remember correctly. And so there's less movement. And so the hypothesis that I put together is as this fault moves, the sand in the Coconino had to be wet. It had to be filled with water. It couldn't have been hard rock. But as this fault energy moved, it actually caused the sand to be injected downward into the Hermit Formation.
So do you think that was post-flood event or near the end of it?
Probably near the end of the flood, or
Okay.
just after the end of the flood is when the Bright Angel Fault moved.
So then you have this fault, and then the Coconino still wet.
Yep.
It fills in those cracks. Wow, that's
And
interesting.
so I actually published this in a conventional journal, Sedimentary Geology, in 2010. Ray Strom published it with me. And the thing that really convinced the editors that I was onto something was the orientation of the cracks. And I'm not sure why they're oriented in this direction with the fault. We need to do some structural geology analysis on that to figure that out. But they definitely have a preferred orientation. They're not random. And the statistics show that too. And because they have a preferred orientation, that means they're not mud cracks. Mud cracks, go all different kinds of directions.
Oh yeah.
And so that convinced the journal that I was onto something there. But here's a conventional view of how this might happen. So this is kind of what I might have proposed in sedimentary geology. But you get the Hermit Formation laid down, you get Coconino Sandstone laid down, and then you get some time to pass. So the time that passes is about 225 million years before the Bright Angel Fault happens. And the faulting is, it's hard to tell, but probably somewhere in the neighborhood of 50 million years ago is when most people think that big movement on that fault happened. And so you have the earthquake penetrate through here, and you have these sand-filled cracks that form. Now, that's all well and good, and I actually explained this one year at the Geological Society of America conference to a geologist from Grand Canyon, and they were all excited about this until I told them what the problem was.
Just one question.
And so this is the question that I ask: how could the Coconino Sandstone have remained soft for more than 225 million years until the faulting occurred? And so there's a time issue. I think there's really convincing evidence that the sand was soft when it was injected downward, but there's a time problem. And so here's what I really think happened. So we have the same kind of slide here. Here's the alternative view. We have the Hermit, the Coconino, probably made very quickly during the flood, so not much time is going to pass. We have the Bright Angel Fault happen, and now we're going to make it happen a little bit faster. And I think this overcomes the time problem. And I think this is really the only good explanation. So
Yeah.
these things really argue that there are not millions of years of time represented in rocks of Grand Canyon. It can't be there.
Wow, that's fascinating. I've never heard that, and I think our
Yeah.
viewers are enjoying hearing about this as well. I saw one comment saying this
Yeah.
is
So
really cool.
that was really fun to figure all that out, and to be
Yeah.
able to interact with people on it too. So this next one is something that Leonard Brand has worked on, and he's really the expert on it and has made these observations. But you can actually see these tracks if you go down Hermit Trail. Hermit Trail is a pretty common trail that people walk down. And as you're walking down through the Coconino, you get down toward the bottom third of the Coconino or so, a lot of these tracks show up. And the tracks always go uphill. So the top of the slide is up, the top of the slope here. I think these dips in here, if I remember right, are right around 22, 23 degrees, somewhere in there. But anyway, the tracks show that these animals are supposed to be climbing up the slopes, and yet they go sideways. This one goes sideways. Their toes are pointing uphill, but for some reason they're kind of going off in a weird direction. And here's another set of tracks down here. Same thing. And this is very typical to find this in the Coconino. I think only in one example people have found them going downhill. Almost all the tracks always go uphill.
Really?
Yeah. And so the other thing that happens is sometimes these tracks will disappear. That it's like something just picked them up off the crossbed slope, and they'll suddenly start in places as well. And Leonard Brand, what he did is he actually used salamanders and made tracks in dry sand, made tracks in damp sand, and conventional geologists argue that most of these tracks were made in maybe some damp sand, or maybe that's how it was preserved. But the problem is the tracks made in damp sand really don't match the Coconino tracks. And even the tracks in dry sand don't match the Coconino tracks very well. And so Leonard Brand's brilliant. He took an aquarium, filled it up with water, and put this sloping, sand dune in the aquarium, and put these salamanders in there, and made them, make underwater tracks. And the underwater tracks matched the Coconino tracks the best.
Huh.
And he published his work in conventional journals. Actually, there's 2 conventional journal articles from Leonard Brand on these kinds of experiments that he did. So really, really some nice top research in that area.
Hey, Dr. Whitmore, before we move on to the next one, I have David McQueen had a comment related to the tracks. Said, from the viewpoint of flood geology, why do we find the footprints of reptiles and amphibians in the Coconino, but do not find their bodies?
Yeah, that's very, very, very interesting question. It's nice to hear from Dave. He was my professor long ago out at ICR, and so nice to hear from him. But yeah, it's weird, but we don't find very many body fossils in sandstones for some reason. And it's not just Coconino, it's many other sandstones too. There's one example of an amphibian, I think, that was found in England. A guy found a void in one of these sandstones, and he had the frame of mind not to destroy the void with his rock hammer, but he filled the void up with some latex and then pulled the latex out of the void, and it was a shape of this amphibian that had been preserved, but the bones had disappeared. So really interesting, and those are some of the only ideas that we have of what some of these animals might have looked like. We're not sure if they're amphibians or reptiles or exactly what they were. Many people claim that there are raindrop prints in the Coconino, and I pointed this out earlier. This is what raindrop prints look like in mud. And most people think of raindrop prints like that in mud, but many people don't realize that when it rains in sand, you don't have the craters. And remember, the Coconino is a sandstone, right? And so here are some of the so-called raindrop prints that you might find in the Coconino. This is typical. This is over in the Ash Fork, Arizona area. And this is looking at the bottom side of the slabs. So the rocks peel up very easily, and you can see the bottom sides. And the interesting thing is, notice that all these things are in lines. And, you know, when it rains, it doesn't rain in lines like that. And oftentimes when you find these so-called raindrop prints, that's what you're finding. I don't know what these things are. I have a few ideas, but I haven't been able to run the experiments to reproduce these things. So I don't know what they are, but they're not raindrop prints. So I think that's another myth. Okay, frosting. Many people claim that the Coconino is frosted, and indeed it is frosted. Here's what frosted grains look like. If you leave a bottle, glass bottle out in the sand dunes, the sand blowing against the bottle will frost it a bit. I was out in Anza-Borrego Desert a few years ago with students. We had 2 brand new Suburbans, and we got stuck in a sandstorm. And the glass on the Suburbans and the paint was frosted from the sand hitting it, right?
Now, can you explain what frosting is?
Yeah, so frosting is just little pits. So it destroys the nice, clear quartz look. So these grains are frosted. This one right here is not frosted as much, so it's a little bit more translucent, but all these others are pretty well frosted. So there are a couple ways that sand grains can actually be frosted. They can be frosted by running into each other, just like sand runs into a bottle. But here's the interesting thing. When you have small sand grains, the mass of small sand grains is not sufficient enough so when they run into each other to mechanically frost the grains. And scientists who study deserts have found this out by, studying modern deserts. And the grain size of the Coconino is too small for frosting to occur mechanically. So it's not true that these grains have been frosted by running into each other in a desert. Grains do not get frosted underwater, so there's not enough. The water slows the grains down, so the collisions aren't as violent underwater. So we looked at these grains with a scanning electron microscope, and that's what these pictures are down here. And the scanning electron microscope shows the frosting is not mechanical, but it's chemical. So this is actually chemical etching on these grains, and that's what causes the frosting. So these grains were not frosted by running into each other.
So can you explain further chemical frosting then?
Yeah, so what can happen is you can get mineral growths on the grains. You can get various dissolution on the grains and so forth to make that surface so it's not nice and shiny and makes the pitted appearance.
Oh, okay.
Yeah, so number 7 here. This is from Sedona, Arizona, and there's a guy named Guy Forsyth standing in the picture there. And this was one of his discoveries, and he found these things and showed me some pictures, and I had to go see him. I was out there within a week.
Pretty cool.
And for him to show these things to me. And what we believe these are parabolic recumbent folds. And this particular one it's about 20 feet from top to bottom. It's huge. And so a parabola is, if I can use this little index card here, parabola, if you guys remember in geometry, is kind of this U-shaped fold, right? And so when a geologist sees a fold on its side like this, we call it a recumbent fold. And so these are parabolic folds because they're shaped like a parabola, and they're recumbent because they're laying on their sides. And I actually had a picture of this fold on a poster at a geology conference I was presenting at. Geologist came up and said, "Oh, parabolic recumbent folds, aren't those, so cool?" And he started talking about them and so forth and how amazing they were. And then he looked up at the title of my poster and said, Coconino Sandstone. Those can't be parabolic recumbent folds. The Coconino is windblown. The point being that parabolic recumbent folds only form underwater. And so what happens is you get the angled crossbeds like this, a current will come along and actually flip the crossbed over. And so these folds form as the sediments are being laid down.
Wow, that's amazing.
Here's another picture of them, and here you can see some that are still at an angle and the top is flipped over. And so again, I kind of show the water current going from right to left here, and the parabola is laying on their sides. But some geologists would say, well, you know, these are just sand dunes that have collapsed. And that's a possibility. Sand dunes do collapse, but this you can trace this bed of folded rock for a long ways, about a half a mile on top of this outcrop.
Wow.
And there aren't any sand dunes that collapse in this direction for a half a mile. So, you know, I think this is definitely one of the things that demonstrates most definitely that this is, at least this portion of the Coconino, is water laid. All right, so how did these folds form? Sand grains have to come apart somehow. And so there's a couple ideas for how sand grains can come apart. They have to be underwater, and then, you know, temporarily the sand grains get pulled apart, and then the folds flip over. So I've done some writing on this. You can find a paper in Answers Research Journal on this if people are you know, interested in some more details on these things, but pretty spectacular. Okay, number 8, dolomite. I remember being with Ray Strom. We were out in the Parashant area. It's kind of northwest of the main part of Grand Canyon. We had to drive out long ways to get out there on a four-wheeler.
Oh, really?
But
Wow.
we climbed up this slope and started looking at the Coconino in this area. And you know, we saw these unusual beds right here where I have the X's, and we weren't even thinking dolomite at this time. I mean, any geologist should be able to identify dolomite in the field, but because we
dolomite?
weren't, dolomite's a marine mineral. It's
Okay.
very similar to calcite. It has magnesium in it though, and if you take some hydrochloric acid and drop acid on calcite, it'll fizz right away. But if you drop it on the dolomite, it doesn't fizz. You got to scratch it and powder it a little bit, and then it will react. And we didn't even think of doing a test like that because why would dolomite be in a sandstone like this? We should have known better. But anyway, Ray took some of this stuff back to the lab, and I still remember opening up the email and dolomite. I just couldn't believe it. And, you know, dolomite is a marine mineral. It only forms in marine settings. And there's 4 dolomite beds there. And that was just the first of the dolomite. We found in some other places these dolomite ooids are like little BBs. And they form, you can find them in the Bahamas in calcite ooids, but they roll back and forth in the surf in a marine setting and make these little balls. And here's dolomite ooids from one place, here's some ooids from another place. So we found these beds of dolomite, we found dolomite ooids, we found dolomite cement, we found dolomite clasts. And you know, I mentioned earlier the book Grand Canyon Monument to an Old Earth. They did have a little section on the dolomite in this book, but they failed to recognize how widespread that we said it was. It
Really?
occurs over an enormous area in the Coconino. And lots of examples of this in the Coconino, which argues that, you know, the vast area of the Coconino had to be underwater to make this kind of mineral.
Right.
All right, and here's some of the dolomite clast. This mineral is dolomite in here. It's been dissolved a little bit. That's what the blue is. But these things are like little pebbles that have been carried along. You can see the white sand grains there. And so these are pretty nice sized class. I don't know if you can see that little rhombus shape pattern there, but that's a
sure, yeah.
dolomite rhomb right there. And so it's not just one kind of dolomite we found. We found it, occurring in a number of different forms.
Wow.
Okay, number 9, mica. Remember that quote from Young and Sturley that I shared? They said, this mica is fragile and it'll be abraded away and, blown off in the wind somewhere. As we started looking at thin sections of the Coconino, and we looked at 400 of them, we sampled the entire depth of the Coconino and the breadth of the Coconino. So we looked at rock all over. In almost every one of those thin sections, we found mica in it. The type of mica that we found was muscovite. So here's a muscovite flake. And mica is a mineral that peels apart into sheets. In fact, you can even do it in your hands. It peels right apart. It's really soft. It has a hardness of about 2.5. It's the same hardness as your fingernails. And so we started finding all this mica. And we're like, wow, this, it's not supposed to be here. And so I had some students that were anxious to do some experiments. And so I said, okay, design an experiment for me to figure out how long mica can last in a windblown environment. So I had the student, he took a pickle jar, one of those big pickle jars, 1-gallon pickle jars. He put the lid on the pickle jar, put an airplane propeller with a motor on it in the lid. And then he put some sand in the bottom of the pickle jar and turned this propeller on, not too fast. We could control the speed. And this sand would spin around the bottom of the jar with the mica in it. And I said, you got to take some samples every now and then to, find out, what's happening to it.
Yeah.
And I think he missed that part because, he's looking at it, a couple weeks later and said, I can't find any mica. And so he redid the experiments and he found out the mica disappears in about 2 days, 48 hours.
Really?
And, in a windblown environment. And so we did some calculations and figured out, how far it would have to travel to disappear and whatnot. And so I had another experiment. He did the same kind of experiment in a pickle jar, but this time he put water in the pickle jar and he put it on a rock tumbler. And so this rock tumbler was going around and you could actually see the mica floating around in the water and the sand and whatnot. And this thing was right outside my office in the lab.
Yeah.
Finally, I had him turn it off after a year.
After a year, wow.
After a year, there was 24/7 and we ran this thing. There was still mica floating around in there.
Wow.
And we kind of took these two studies, put them together and published them in a journal, a secular journal called Eolian Research, arguing that, if you find mica in rock, it has to be waterborne because, this stuff disappears in a desert environment. So we published it in a journal about sand dunes. And, it's in the secular literature. And of course, sample after sample of Coconino, we were finding, really big mica flakes sometimes in the Coconino.
Well, that's awesome. I want to get that link for that publication. Maybe we can share that in the show notes.
So I think at the end of this presentation, I've got a list of most of the references there.
Okay,
There's,
good.
Plenty of stuff there. All right, this is the last one here that I have. The question is, how do you get big sand dunes underwater? And some people might think that, there's no way you could get these big sand dunes underwater. Well, in fact, there's many places known, and marine geologists are well aware of this. There are these things called sand waves. Some of the most famous sand waves are in the North Sea, in between England and Europe. But there are also big sand waves. You might recognize this bridge in the picture right here. That's the Golden Gate Bridge that goes into San Francisco. And this is a radar image of what the bottom of the bay looks like. And there's big sand dunes under there. And the big sand dunes are generated by really strong currents that flow in and out of the bay. And these sand dunes in here, if I remember right, they're about 25 feet high or so. So they're big. This is even more spectacular. This is Long Island Sound. And you see that little black blip right there?
Oh yeah, real tiny. Yeah,
Yeah,
I do see it.
that's a shipwreck.
Wow.
That ship is the size of a football field. And so you can get an idea how big these sand waves are. And
Yeah,
they're
that's massive.
enormous. And, Paul Garner and I have been working on this a bit, and we've identified over 40 places, mostly on the continental shelves, where these things occur. And we don't think that the Coconino exactly represents sand waves, but this is the closest thing that we have. We think the Coconino must have been deposited by really strong sediment-laden currents. Probably we don't have any modern analogs to it at all today. But this is something at least close to that we could point to show that, big sand dunes underwater is very possible. And in fact, they're very common in our oceans today. And so what have we done today? We've looked at these 10 myths about the Coconino, and instead, let's turn this on its head and say we found 10 truths about the Coconino. And these truths, as we look at the conventional model for the Coconino, this data that we found about the Coconino, falsifies this idea that it was made in a desert. And so we have crossbed dips that are really shallow. They don't match up to crossbed dips that we would expect in a desert setting. The grains are angular and not very well sorted. We have sand injectites, which actually requires the sand to be underwater and be injected, filled with water. Leonard Brand has found evidence of the tracks being made underwater. The raindrop prints, we don't think the features there are raindrop prints. We think there's something else. We don't know what. The grains were frosted chemically. The parabolic recumbent folds, those were actually spectacular. The ones we saw from Sedona area. We found the mineral dolomite present, which should not be present as widespread as we found it. We've also found really widespread mica, and we found that these big things called sand waves are pretty common on continental shelves. And so you put all these things together, and we see that many features commonly cited about the desert origin of the Coconino are false. When you actually get your boots on the ground and get your hand lens and go out and look at the rock formation, it doesn't look anything like that has been purported in the literature. Instead, a lot of these features argue that this is an underwater deposit. And so, what we found in the Coconino has implications for other cross-bedded sandstones like the Navajo. The Navajo maybe is even a more well-known sandstone. It's the nice big cross-bedded sandstone that you see in Zion National Park and over many places in Utah. And we've started a little bit of research on the Navajo, and we're finding some of the same things. So that's going to be the next chapter. So we're not quite ready to publish some things on that yet, but that's coming down the pike.
Yeah.
And we should have expected it, but when we actually do the research and get out there and collect the rocks and do the science, we shouldn't be surprised that we found out there's abundant evidence to support God's word. And I think that's where I want to end today, that, when we go do the science, it supports the word of God and what we read about the flood.
Amen. Well, this has been a amazing presentation, and I know our viewers are loving it as well. And thank you so much, Dr. Whitmore, for coming on.
Yeah, you're welcome.
And
you can find a full-length paper on this presentation. Actually, the ICC, the International Conference of Creationism, belongs to Cedarville University now. And we have put all the proceedings on Cedarville's website. You can go to International Conference on Creationism.com and find the proceedings there. Or you can go to Cedarville University Library and find a link there. So the next ICC conference is going to be in Cedarville, in fact. So.
Oh, is it this year or the following year?
No, it'll be in 23 is when we're going to have the next conference. So.
Oh, that's great. That's so awesome. You know, and any of our viewers who some of this info is new, I would just encourage you type in Coconino Sandstone, and you'll see almost all of these myths in many of the secular articles. And we got to get this out there. One question that comes to mind before we let you go is how are the other secular geologists receiving some of this research? Or are some kind of rethinking their view? Or
I don't know. It is sometimes it's really frustrating. I like going to conferences and engaging with people, but sometimes they just go like this. I don't see anything. And it it is very frustrating sometimes. But one bright spot, a very well-known geologist came by my poster one year, and if I said the name, every geologist would know exactly who he is. He's made huge contributions over his career. I think he was well into his 90s when he had a cane and whatnot and was walking very slow, but came up and looked at my poster. And I think I had thin sections of the Coconino showing the angular nature and the pore sorting and stuff like that. And he looked at things and said, yeah, I think it's about time we reconsider this sandstone. And that really made my day, right? Coming from a geologist like that. So, yeah. So he had a career of well over 50 years of publication. And for him to say that was really encouraging.
Absolutely. So. Yeah, praise God. And I mean, and I think other people, Lord willing, will begin to see that. And of course, we know God opens people's eyes to see things that confirm his word ultimately and to put their trust in him and in his word. I just want to thank you so much again, Dr. Whitmore, for coming on. And I want to encourage all of our viewers and listeners to just like, subscribe, and please share this page, Engage Truth, on YouTube or Engage Apologetics on Facebook. And I don't think you're going to find very many videos like this and very many other apologist pages, because I can tell you a lot of apologists aren't even touching this issue. But I really hope we can get this research out to more people, and more people can engage with the truth. So thanks again for watching, guys, and please share the show so more people can engage.